thank you very much for giving me this opportunity to present this material. I'll be talking about algorithms for removing boundary problems for Navier-Stokes equations. And this is class of problems when we do not know location of the boundary. We have to determine location of the boundary as a part of the solution procedure. So we have to determine flow field and position of boundaries. Now, before I go into details, let me show you where I am. So this red spot here is London, Ontario, which is between Toronto and Chicago. Can you see my cursor? Can you see my cursor? Hello? Can you hear me?
Yes, sir, it is visible. It is visible. And you are audible clearly.
Okay, so I'm close to Toronto, as you can see here. So it is close to midnight, my time. I understand that it's around 8 o'clock or 9 o'clock, your time. So it was a long day. So I hope my speech will be sufficiently detailed in spite of late time. Okay, so let me start with discussing flow physics or features associated with flow physics. So this is an example. On the left side, I have fluid A, which is green fluid, fluid B, which is blue fluid, and there is interface between these two fluids. So there is a distinct change of a type of fluid across the interface. And then I have solid wall, which also can be moving, or the movement can be prescribed, or I may have some form of flutter where movement of this wall is caused by dynamics or by movement of the fluid. So the problem that we have is that we have moving interfaces and we don't know where these interfaces are. We can have colliding braking interfaces. So in my sketch on the left, we have just one interface, but we can have many. Then we can have voids, like empty spaces. Then we have a slippage along the interface, which we have to model it properly. And if you look at the contact point, which is where interface becomes or comes into contact with solid wall, we have so-called contact point, and then there's interesting contact point dynamics. And then along the interface, we may have to account for surface tension, which means that we have to be able to determine curvature of the interface. And then we have various types of solid-fluid interactions. We may have movement of solid objects, and then we can look at it as shape optimization, where movement of the boundary is described by some form of optimization principle. And we can have many other complications like solidification or melting. We may have like combustion front and so on and so on. So boundary, in the simplest case, boundary conditions involve continuity of velocity vector. And then we have to have balance of forces at the interface. So on the left-hand side, this double dash denotes tensor, and n is normal unit vector. And k here is mean curvature, which is surface divergence of normal unit vector. So these are boundary conditions that we have to incorporate into our algorithm. Now, if you look at mathematical difficulties, we have nonlinear field equations with high-order operators. We have nonlinear boundary conditions of complicated form. Then we have nonlinearity due to moving boundaries. So the fact that we have moving boundaries and both field equations are linear still makes problem nonlinear. We have boundary layers near these interfaces. And of course, we have irregular variable solution domain. And we can have changes of connectivity, which we call like topological bifurcation. We can start with simple connected domain, end up in multi-connected domain. Then we have, of course, large interfacial distortion, cusp-like interfaces, folding interfaces, multiple interfaces, crossing interfaces, and so on and so on. And of course, if we have surface tension, if surface tension plays an important role, we have to have a high accuracy required to get curvature of interfaces. And then we have singularities at contact points, so we have to do something about them. And then we can have several physical instabilities that may occur at interfaces. And this instability may be characterized by different temporal and spatial scales. And in interfaces, typically we need to have absolute temperature, or we have to determine absolute temperature, so this has to be quite accurate. And probably, if you know, in computational simulations, boundary conditions play enormous role. So we can have proper treatment of field equations, but boundary conditions may defeat our algorithm. So now let's look at theoretical issues. So first, we have to look, does the solution exist, and what are existence conditions? Is solution unique? We know that fluid mechanics is full of non-linearities, which means solutions generally are not unique. We have 1, 2, 3, or several solutions for the same set of parameters. Then we have to think what it means to have well-posed problem when boundaries are moving. And what is character of the problems? Is it like elliptic, hyperbolic, parabolic? And then we have to look at stability of solutions. So we have to look at stability of algorithms and physical stability of solutions. Okay, so if you look at these problems, I have green fluid, blue fluid, and interface between them. We can look at two types of formulation. Eulerian methods, where we are looking at fields, and Lagrangian methods, where we are looking really at elements of fluid. So in the discussion, I will start with Eulerian methods. So Eulerian formulation, it means that coordinate system which we use is either stationary in the laboratory reference frame or moves in a prescribed manner which is not related to movement of fluid. We just impose certain movement of our coordinate system. What is characteristic is that fluid travels between different computational cells. So computational cells do not contain the same fluid elements. The issues that we have here is what is the most suitable formulation of the field equations. And we can have primitive variables, stream function vorticity, velocity vorticity, conservative, non-conservative formulation, and so on and so on. So depending on applications, certain way of formulating problem is better than others. Then what is most suitable discretization? Finite difference, finite element, finite volume, spectral, discontinuous Galerking, and so on and so on. So again, depending on the type of a problem, some of this discretization may be better than others. And what is best strategy for interface tracking? We have to be able to determine position of interface. And if you look at Eulerian formulation, we can work with adaptive grids, and I'll discuss in details soon what the issues are. And we can look at fixed grids. And in case of fixed grids, we have to have surface tracking or volume tracking, which leads us into immense boundary conditions concept. So if you look at that adaptive grid and fixed grids, the concepts go back to 50s. So like 70 years ago, and they are being rediscovered every couple of years. And immense boundary conditions extremely popular these days, but the concept goes back at least 60 years. Then we have mapping methods and various special methods. Okay, so let's look at fixed grids. The basic idea is when I have fixed grid system, so you see this kind of straight lines, and I have interface going between on this grid. On one side of interface, I have green fluid. On the other side, I have blue fluid. And somehow I have to determine movement of these green particles and blue particles through this grid. So grid is fixed, but interface moves. So what are advantages of this concept? Interface may undergo large deformation without, in principle, loss of accuracy. So it's very easy to consider large deformations. It is relatively straightforward to handle multiple interfaces. The problems or challenges are how to calculate location of interface accurately, because if I have this final size grid, the interface will be smeared on this grid, so we will not have precise location of the interface. Okay. Then you can look at adaptive grids. So adaptive grids, if I have interface, then I construct a grid where one of the grid lines overlaps with the interface. So I have precise location of the interface, but as interface moves or deforms, I have to reconstruct grids. So a lot of grid generation, and this will create limitations on what can be done. So advantages is we have very sharp resolution of interface. We know precisely where interface is. Problems, difficulties in adjusting grids to follow highly deformed interface. And my experience is that using this concept, like 75% of computational time was spent on adjusting grid and only 25% on solving field equations. But conceptually, this is a very attractive direction. If you look at mapping methods, look at those special methods. So I have my physical domain, and I don't know what the shape of the domain is, but I can map it onto regular domain, let's say square or circle, and my mapping is one of the unknowns. So this leads to, this is limited to classes of geometries that do not lead to singular mappings and lead to complex form of governing equations. Okay? But they are very attractive for certain types of applications. The mapping methods, then if you look at special methods, we can look at boundary integral methods, vortex methods, contour dynamics, front tracking, and many others. So a lot of specialized methods have been developed, and depending on application, you may want to look at these specialized methods. Okay, so now let's look at fixed grid methods. So the first concept is surface tracking. So this is my grid. Interface somehow moves through the grid. And then on the interface, I have points, and I follow movement of these points. And I reconstruct interface by doing interpolation along these points. So I can have kind of arbitrary points on the left side, and I can have some other type of representation of position of the points on the right side. So with this concept, we can track small-scale structures on the interface, but can be expensive because we have effectively two grid system. One is my reference rectangular grid, and then I have a set of points that give me position of the interface, which is my second grid. And here the best known application is marker and cell method, which essentially we say if we have these points in a cell, it means interface is there, and there are no points in a particular cell, it means there's no interface there. And based on this information, we can reconstruct the interface. Now, another concept in surface tracking is volume tracking. So this is my interface on the left side, and I know that my interface is in the cells that are dashed. Okay, so I know roughly which cells contain my interface. So this is basis of marker and cell method. If I have cells that contains, let's say, blue elements and green elements, it means interface is somewhere there. And then the question is how to reconstruct this interface, because the only thing I know that interface is somewhere there. And there are various algorithms. There is something called SLIC. So I move in time in two steps. So in one step, I represent my interface using vertical segment. In the second step, using horizontal segment. And out of it, I reconstruct position of the interface. Another way of reconstructing interface is Solavov, so which is a fraction of volume method. And here I create a quantity f, and f is 0 if my cell is empty, f is 1 if cell is full, and if f between 0 and 1 means I have cell with interface. And then I have kind of simple diagram or simple equation describing propagation of interface. On this basis, I reconstruct the location of the interface. So if I look at volume tracking, we do not get details of interface, so no shear stress, no surface tension, but we can treat multiple interfaces, and method is very robust. So depending on application, this method could be suitable. So with an application, so you can see on the left-hand side, I have a container with, let's say, water, and I suddenly open up the gate and I look at formation of the surge of water that is associated with movement of this water under the gate. Okay, because so you can see this is time-dependent simulation, and this was done in mid-50s last century using computers that were available at that time. And computers that were available at that time is much worse than what you have in your cell phone right now. This is another simulation. So we release block of water and we look at impact of this water, let's say on a building, and we want to determine what damage it can cause. So, in this simulation, we don't need precise details of interface. And within this volume tracking or surface tracking, we can get a lot of physics. Adaptive grid methods, so here a lot of grid generation, and the interface we have involves kinematic condition, balance of normal forces, balance of tangential forces, and continuity of velocities, lots of boundary conditions. In case of steady flow, we use something called Picard iteration. So we assume shape of boundary, we construct grid, we solve field equation with one of boundary conditions omitted, and we use this omitted condition to determine if my shape of boundary is correct. And if not, we adjust shape of this boundary until we can satisfy all conditions. We can formulate the same problem by parameterizing grid, and then we have direct solution for the flow equations and the position of interface at the same time. In case of unsteady flows, we use kinematic condition to propagate interface, and lots of details here. And of course, we have to have dynamic grid because interface moves, so we have to adjust grid. This is an application of coating, of a coating process. So we pump the fluids through a nozzle, let it flow here, and we look at coating of this interface, and we try to determine the best conditions for proper coating. Okay, so it's Eulerian methods. Now let's look at Lagrangian methods. So we have Lagrangian formulation of the field equations. So coordinate system moves with the fluid, and each computational cell always contains the same fluid. An alternative is particle methods. So I will discuss Lagrangian methods and particle methods. So Lagrangian methods, advantages, well, we know precisely where each mass element is, so we can follow material interfaces. Free surface boundary conditions easily applied. Detailed structure embedded into the flow can be zoned more precisely. And nonlinear convection terms in the equations of motion are absent. We don't have nonlinearities. Problems, we have mesh tangling associated with large deformations and numerical inaccuracy due to highly distorted meshes. And this is an example. So I have volume of fluid, the top layer moves to the right, bottom layer moves to the left, and the middle layer, the mesh in the middle layer gets highly distorted, and eventually we lose accuracy. So we have to do, so this method can work up to certain time interval, and then you have to do something because you are losing accuracy. So this was strictly Lagrangian methods. Now, because of mesh tangling, we can use reasoning, and then eventually we can end up with free Lagrangian methods. So this is an example of grid tangling, and obviously at a certain moment we have to do some reasoning, or we have to fix the grid because we are losing accuracy. So you look at reasoning. So I have distorted mesh, which is no longer acceptable. So I specify new mesh, and I have to transfer information from old mesh to new mesh. And how I do this transfer, if I do it poorly, I lose a lot of information. So if you look at this distorted mesh, so then I have to do this reasoning. So I specify new mesh that has better properties. and then I have to do remapping, so transfer information from old mesh to new mesh. So if you look at general reasoning, I have arbitrary mesh, which is expensive. I have lots of numerical diffusion or numerical inaccuracies. And then I can look at so-called conservative reasoning to deal with errors. Then I can focus on meshes preserving topology. So I rearrange the mesh, but I maintain the same topology. So fixed connectivity. Then I can have continuous reason. At every time step, I do a little bit of mesh adjustments. And I can go into generalized topology. So mesh at a given moment is totally topologically unrelated to mesh in the next time instant. So if you look at free Lagrangian methods, essentially I have a set of points. And on this set of points, somehow I have to formulate proper field equation. So here I can change connectivity with the grid. Some mesh points can be reconnected, added, or deleted. So I can insert new points or subtract points depending what I want. And the best grid is a called Voronoi-Delanoy mesh because it has best packing. And eventually I can abandon grid completely, and I can approximate operators on a set of disorganized points. So I do not assume any relation between these points. I just have a set of points, and I have to discretize operators somehow. And if I do this, then I run into problems with neighbor searching algorithm. Because if I look at this point, probably I should discretize operator using closest point. So if I used to look at this point, I should not be using information from this grid points to approximate operator here. So I have to have effective neighbor searching algorithm. So it's an example right there of instability. I have free fluid layers, and when I let them go, so weight of this fluid causes adjustment. And you can see I have large deformations. I have to do a lot of changes in the grid to maintain accuracy. And this is shattering of a droplet. And again, you can see as droplet deforms, I have to do a lot of grid adjustments near the droplet where I have large deformations. Okay, now let's look at particle methods. So particle methods, the concept comes from molecular dynamics and was introduced in early 50s. In fluid mechanics, we use particle mesh combination. So it's Lagrangian Eulerian concepts. We use grid to compute forces and use particles to simulate convection. And the more best-known algorithm is particle in cell algorithm, PIC, which was created in 1955, so a long time ago. So you see I have fixed grid. In this grid, I have green particles and blue particles, and I treat these particles as mass element, and I look at forces acting on these particles, and movement of these elements or these particles simulate convection. But then I need forces acting on these particles, so here I use grid to determine forces acting on these particles. So I have to transfer information between particles and grid and back to particles. So the problem with this PIC algorithm is that I have double grid system, kind of regular spatial grids plus many particles. I have large numerical diffusion or numerical inaccuracy due to momentum transfer, because I have to go from grid to particles and back. I have numerical noise because properties change in discontinuous manner between different cells. And I can simulate range of variation of properties. And this is limited by number of particles. I could have millions of particles, but it's not practical. So I always have finite number of particles, and this limits my accuracy. And spatial resolution is limited because of fixed grid. I can have very small grid, but again, this increases cost of computations. Remedies, better interpolation. So one concept is finite size particles, and assign more information to the particles, so-called full particles models. So all these concepts came from in early 50s, and they came out of Los Alamos. All better reduction algorithms, non-uniform adaptive grids, and so on. You can see these concepts kind of keep reappearing. better convection algorithm, non-uniform adaptive grids, and so on. So this is simulation. This is droplet impact on a shallow pool of water. And you can see, what happens, how this droplet collapses, and when the fluid is ejected from this layer of fluid that was under the droplet. So this may not be impressive to you, but this was done in mid-50s, so it was 60 years ago, using computers at that time. Then there's one more concept, which is smooth particle hydrodynamics. I essentially work with a set of random particles. I have green particles, I have blue particles, and I estimate gradients from interpolation schemes without requiring any grids. I just take neighboring particles and I set up some methods to estimate gradients which are necessary to get equations of motion. So the issue that we run here is interpolation from disordered set of points. Then we can, of course, assume random distribution, use Monte Carlo methods to get continuous distribution, and so on and so on. So we can, put many concepts into this so-called smooth particle hydrodynamics system. This, I think, brings me to the end of presentation. I have 30 minutes and just ran right on time. So what you can see that there are many concepts. The concepts go back at least 50 years. The algorithms that result from this concept are somewhat problem dependent, so there's not one algorithm that can do everything. You have to adjust algorithm or select algorithm on the basis of needs of your particular problem. Accuracy is uncertain. Typically, it's probably first order, but I work on development of spectrally accurate algorithm, and I have certain methods that I can maintain spectral accuracy on moving grid. And new ideas are required. So what happens, main problem is geometry. And what happens when the concept that I presented, they have been around for a long time. They are being rediscovered every 5 years, and probably know about this immerse boundary conditions concept, which are very popular these days. But we are really proposed in 50s, so 70 years ago. So many of these ideas are just not known. They're being rediscovered every 5 years. So hopefully this presentation will give you a summary of overview what is available, and rather than rediscovering the same things again, maybe you can just try using what we know and maybe improving with algorithms that are available. So with this, I would like to finish. Thank you very much.